Okay, so this video refers to the second part of the Lecture 5 lecture on equilibrium of a rigid body, and it's specifically looking at two force members. So a two force member, you'll be surprised to hear, just like the diagram on slide 23, is a member that is acted on by two forces. So if we've got two forces, only two forces, and we want to work out our resultant force, if we join the points where these two forces are acting, then we can say the resultant force will be, at each point, will be equal in magnitude and opposite in direction, and will be acting along the line that joins those 2 points, in order for it to be in equilibrium. And that makes it a lot simpler to solve equilibrium equations on rigid bodies where we've got some strange shaped members, or where we may not have all the information at one point, but we have lots of information at the other. So, for example, solving an equilibrium analysis solving a problem using this technique. I'll do the first example from Lecture 5 that utilises two force members, which begins on slide 27. I'll just draw it, I'll show you how to solve it, and then there's one for you to practice. So this is the question as it's presented to you, and you're asked for the support reactions at A and at C. So the first thing we do is we draw a free body diagram for this question. So if I jump to a new page just so I've got some room, you'll see I did draw in the types of joint. Both A and D are pin joints. So we've got our beam, arc halfway along. We know that's 1.5 metres and 1.5 metres. We know we've got 4 kilonewtons acting down here. We know that there's a force coming here at that angle. Now it's coming at that angle because you'll notice that CD in the diagram is a two force member. So we may not know what's happening specifically at D. We may not know the magnitude of the forces in the X and the Y direction. We may not know the size of these forces. But we know that the resultant force at C and at D is going to be equal in magnitude and opposite in direction. So in fact, from this beam we would have two forces, one going that way and one going that way, and we're interested in this second force, the force which we could label force C. So we're going to include that in our diagram, force C. At A, it's a straightforward pin joint. It's going to have two components. It's going to have AX and it's going to have AY. And if you're not sure which direction to put any of these arrows in, if you assume one direction and if it comes out negative, it's the opposite direction, just as we've done previously. We're given 45 degrees there. That 45 degrees you can work out because you've got dimensions. Here, I've missed the dimension, sorry. You've got 1.5 metres there. So you've actually got an isosceles triangle. They're the same length, which means that has to be 90. If they're the same length, that's 45 and that's 45. So now we can start to solve that using our equations of equilibrium. So the sum of the moments, and we'll take moments about point A, and we've chosen point A because we've got two unknown forces at point A. We've got AX and AY. So if we take moments about point A, we can ignore both of those. That's going to be FC sine 45, so that component, times by 1.5, and that's going to be trying to go anti-clockwise, so we'll call that positive, and it's going to be minus 4 times 3 metres, so our initial force that we were given as well, and that's going to equal 0. So we can say FC is going to equal 11.3 kilonewtons. I can then put that back in and I can start to do forces, sum of forces in x and y directions. So sum of my forces in the x direction is going to be AX plus 11.3 cos 45, which equals minus 8. So the assumption for the direction I've labelled AX going in is wrong, but that doesn't matter, we'll still get full marks for that question. The sum of the forces in the y direction is going to be AY plus 11.3 sine 45 minus 4. That equals minus 4. Sorry, I've written these slightly wrong. That could be very ambiguous, very confusing for you. That equals 0. Rearranging that, AX equals minus 8 kilonewtons. That equals 0. Rearranging that, AY is minus 4 kilonewtons. So the negative signs on both of those show that we've assumed the wrong directions for the forces at A in both cases, but we'd still get full marks in our actual question in the exam. There is now a group problem solving task for you to have a go at beginning on slide 30. If you pause the video, have a go, and then come back to it and I'll show you how to solve it. So this is the group problem solving exercise to do with Freebody, to do with equations of equilibrium, drawing a Freebody diagram. You're looking for the horizontal and vertical components of reactions at A and the reaction at B. You've got a two-force member in this question again. So the first thing you do is you draw a Freebody diagram for this. The question started on slide 30 if you're following it from the lecture pack. So if I draw the Freebody diagram first, we're only interested in member AB. A is meant to be a pin joint, and you can see that better on the slides. So we're going to have an AX and an AY. We're going to have an FC. So for force C, you find your triangle, your ratio of how much in the x through in the y by the dimensions again. And this time we haven't got we can't get angles, but we can get we've got 1.5 meters here, and we've got 2 meters here. If we double 1.5, we get 3. If we double 2, we get 4. If we've got 3 and 4, we know that must be 5. Also, we've got 600 newtons acting downwards, and we can label our 1 meter, and we've got 2 meters there, and we've got 800 newtons acting downwards, and then we've got a turning moment of 900 newton meters. So then we need to solve that. The first thing we do, exactly the same as before, is do our sum of our moments. So the sum of our moments about A, again because we've got 2 unknown forces at A, is going to be 3/5 of force C, so this force down here, and it's going to be times 2 because it's acting 2 meters from the beam, and we're only interested in the Y component because that's the only bit that's going to have a turning effect. And that's going to be trying to turn it anti-clockwise, so it's positive. We've also got minus 600 times 1, and I appear to have stayed with the red pen, sorry about that. And we've also got minus 800 times 4. They're both the forces that were given, and they're both trying to turn it clockwise, so they're both negative. If you're following in the lecture notes, it actually says minus 400 times 4, that is a typo. The answer still comes out correctly in the PowerPoint. And we've also got minus 900 because we've got a moment that we've been given that's trying to turn it clockwise, and that should all equal 0. So I can then rearrange that, and I can find my force C to equal 3.92 kilonewtons. And in fact, when I'm using it in my equations, because everything else is in newtons, I'm going to keep it as 3,900 and 20 newtons. There's a little bit of rounding in there. So then I'll do my sum of my forces in my x direction, which is going to be AX, and it's going to be plus 3,920 times 4/5. So I can rearrange that to find AX, and AX will equal minus 3133 newtons. Similarly, my sum of my forces in the y direction is going to be AY. It's going to be plus 3/5 of 3,920, and then minus 600 and minus 800 for the two forces we start with that are acting downwards. That equals 0, so AY is going to equal 950, and it's going to be minus 950. So again, the two directions that we assumed at the start for AX and AY in our diagram are both incorrect and the wrong way around. So that concludes the two force member section of Lecture 5. It's the two examples of questions that you could be asked. We'll go on to look at some other questions. Other questions may have two force members in them still, but they're the introductory questions over. The next section looks at constraining systems and trying to stop things moving and what different joints do and how they affect the movement of things. But that concludes the two force member section of Lecture 5.